Okay, further gave an example of what would happen when the process so the observation periods are not aligned with the I guess with the some periodicity, right? You're saying that there is some what you have in mind, it looks like, is that there is some um uh, frequency of certain fluctuations in the process, but that's not how we observe. I think if we have enough observations, we still should be able to get it. I need to think more of it. Let's move now. We can think about it during the tutorials. I think in theory, if we have if we have enough history, then we can back out the true process. Um, So this lecture is going to be based on these two books, which are considered to be uh, classical books on machine learning. This is an undergraduate level textbook that the authors use in Stanford, and this is a graduate level textbook. I will mostly use the slides on this chapter. Why I deviate from the Elliot Timmerman book? Because I think they don't explain well lasso and reach and like shrinkage methods, while these guys explain it super well. So let's rely on this book. So let me start with some motivation. And actually, this motivation is related to what Fedor asked me last lecture a week ago. When I was discussing bias variance trade-off, I want to discuss it again. So if we think about linear regression and the associated Gauss-Markov assumptions, let us think about the linear regression and associated Gauss-Markov assumptions. So the assumptions that the five classic assumptions that we make in the context of the linear regression are that the model in the population can be written in a linear form where epsilon is the unobserved error, random error, then observations yi, xi randomly drawn from the population. Then in the sample and in the population, there are no exact linear relationship among inputs xi, so the whole column, the whole matrix of x is invertible, and the error has zero mean given the predictors, so or covariates, so there is no covariance between error and regressors and homoscedasticity. So these are the usual assumption. So the classic assumption, Gauss-Markov assumptions, and under these assumptions, we have the classic Gauss-Markov theorem. Again, which is this is what Fedor referred to during the last lecture. Under the Gauss-Markov assumptions, the ordinary least squares estimate beta hat is the best linear unbiased estimate of beta, in the sense that beta hat G have the smallest variance among all linear unbiased estimates of beta. Let us talk a bit more specifically about what we mean about by the best linear unbiased estimate. So let theta A transpose B be any linear combination of parameters. For example, predictions of this form. So more generally, this is A T A P beta P. The OLS of estimate of theta is equal to this. Then under Gauss-Markov assumptions, 1, 4, we don't need the assumption 5 about homoscedasticity. Theta hat is an unbiased estimate of theta. If we calculate the expectation of theta hat, we get A transpose beta. Now, if x is fixed, then theta hat is a linear function theta 0 y of y if we fix this part. So this we can assign theta, sorry, C0. Now consider any other linear estimator, theta tilde, that is unbiased for theta. That is, we have this. Then a version of the Gauss-Markov theorem is that the variance of theta hat is not larger than the variance of any other unbiased, linear unbiased estimate for theta. And this is what we mean that this OLS estimate is the best unbiased estimate
It's
of, yes?
it's the best in terms of efficiency, right?
Uh, you just you just used one word, the best, to replace it by the other word, efficiency. What do you mean by efficiency?
Well, if the estimate is efficient, it means that it has well, uh, it means that there is no other estimate which gives us less variation.
Less variance. Yeah, you can say if you define efficiency this way, okay, good, fair enough.
Okay.
But this is what was written here.
Okay.
Okay, now let theta double tilde be some estimate of theta. Let's calculate it, its mean squared error defined like so, where the expectation is taken across all data sets x, y. We do the trick that we did in the lectures before, and this is the standard trick here. We add the mean, subtract the mean or the expected value of theta tilde. Then we open the brackets. Here we have this term squared, this term squared, and then the 2 multiplied by combination of these terms. And this is 0. Well, this is 0. And because this is non-random, we took it out, and we can take it out here, and the expectation of this is 0. And then what we are left with is the sum of this term and this term. This term, by its definition, is variance, and this term is bias squared. So again, the Gauss-Markov theorem implies that the OLS estimator, like theta tilde, has the smallest mean squared error of all linear estimators with no bias. So I want to emphasize here and be now alert why I'm giving this example. What the Gauss-Markov theorem says is that consider all estimators theta double tilde for which this term is zero. Then the OLS estimator would be the one that has the smallest this component, which would imply that the mean squared error of OLS estimate would be the smallest among all estimators with no bias. So we go from the definition of the property of variance being the smallest to the property of the mean squared error being the smallest. So let me repeat. I mean, it's written here, but it's worth repeating. OLS estimator has the smallest mean squared error of all linear estimators. However, there may exist a biased estimator, an estimator for which this is not zero, and for which the whole mean squared error is lower than the one for OLS. Why? Because this component can be even smaller. And that's where we are going to be doing lots of explorations. I talked about it last time, how this bias versus variance is a fundamental, bias versus variance trade-off is a fundamental fundamental issue of machine learning. And so I'm bringing it up again. So this was about the mean squared error for the estimate, for the parameter, sorry. We can also look at the prediction error, or what we called the risk. So we defined it as risk in the earlier lectures. This now expectation is taking over all data sets, which we use to estimate beta tilde, and then over all y zeros and x zeros. So we do the full expectation over all things. Then we can write it like this. And that basically looks like MSE. Well, it's written here. This, which is, we can say that this is our theta double tilde from the previous slide. Then the only difference is that there is the sigma squared, which we call the irreducible error. But still, in terms of expected prediction error, we have the same bias variance trade-off. So we have the bias variance trade-off both for some linear combination of coefficients estimate and for the risk or prediction error. And one note about this irreducible error, it's called irreducible error, meaning that it's irreducible given our model. But if we have a different model, then we potentially have a different error. So that's another area of exploration. But we rather right now focus on this variance bias trade-off.
And about the second term, if beta tilde is equal to beta, then the second term is equal to sigma squared.
This one.
Yes.
No, it's equal to, you mean if a beta tilde is equal to beta?
Yes.
Well, it's equal to variance x0 beta, whatever it is. If beta is a number, then it's not random. Then if this is not random either, then it would be equal to just squared. If it's random, then it would be equal, it's going to be equal to whatever. So it's not sigma squared. Does this make sense?
Yeah. We would need an infinite number of observations for it to be equal. Like it should be approaching sigma squared, I think.
This term?
Yes.
No, I mean, think about, suppose x0 is 1, beta is 1, and there is only 1. So suppose that is just equal to beta x0, and x0 is 1 for any error, and the true beta is 1. Then what is this variance? Regardless of what the variance of error, this is 1. It has nothing to do with the
I
error.
mean, if the number of observations approaches infinity, this term should approach sigma squared.
I guess further means
No,
asymptotic convergence.
no. I'm totally lost. Sorry, I'm not sure what you're talking about, because just I'm giving you an example. Imagine that the true model is 1 plus epsilon x0. Then this term is 1 always, while the sigma squared can be whatever we assign. Imagine a different model. Y0 is epsilon 0, and we throw in some regressor, 0 multiplied by some regressor. Then if we know that beta is 0, then this term is 0 again, while the error can have any variance we want. So I'm not sure what you have in mind. Does this make sense? I don't see where you're confused. What
Sigma squared, it's the variance of error, right?
yes. Yeah, right.
Yeah, okay, yeah, so not of the y. I guess that was the misunderstanding.
Yeah.
Okay. I see. Okay, got it. Right, it's not the variance of y. Right. Well,
Oh.
uh, yeah, from here. Okay.
But shouldn't the variance of y be equal to the variance of the error term?
I think it depends on, not I think it depends on this guy. If X are random, then even if they are not correlated with epsilon 0, then the variance of Y will be different from the variance of the error. Just think about it. Suppose this is a random variable and this is a random variable. Even if they are not correlated, the variance of all this term would definitely not equal to the variance of just variance of the sum of two random variables definitely is not equal to generally not equal to the variance of one of them. Does it make sense?
I suppose.
Okay. Anyway, the point here was that even for the risk, when we consider risk, basically we have the same problem, that there is the variance and there is the bias. And actually, it's very important to understand that this is not related to sigma squared, because this is the term that we will be manipulating now with different methods. And sigma squared is sigma squared. It's whatever. We call it irreducible error. While this component we will be manipulating to make it smaller or larger relative to this component. And if you will, the whole point of shrinkage methods would be making it, manipulating this. Okay, then a couple of several observations. So suppose we have this linear model. If the true relationship is close to linear, then the OLS estimate has low bias, and if we know the true model, with all the, if all the P regressors are the true, there is no omitted regressors and stuff like that. However, no, not however, if in addition the number of observations is much larger than the number of regressors, then OLS estimates will have low variance and good performance on test observations. Now, if we have slightly larger, but of the same order number of observations as the number of coefficients, I mean, number of regressors, suppose we have 10 regressors and 12 observations. Or if we have 10 regressors and 9 observations, then in this case, we have lots of variance and we have overfitting, which I discussed last time, and we have poor predictions. If we have this case, then we cannot even do apply OLS. Basically, we have infinite variance. Also, if P is large, model interpretability suffers. If say P is equal to 1000, well, in some applications it's equal to 1000, but even if it's like 50 or 100, that's already a lot. And OLS is unlikely to give, in practical situations, OLS is unlikely to give exactly 0 for all irrelevant regressors. So we'll always have some regressors flowing around which have non-zero coefficients, but they might not be related to the outcome. And that increases the variance and introduces this spurious correlations. And we are in the situation where some model interpretability suffers. So that's why we come to a situation where we want to, even if the true model is this, with all the p regressors, we want to somehow select only the most relevant regressors in some sense. Or if there are too many regressors and some of them are not related, and the data set is not large enough, we need to have the most relevant regressors somehow select. Or one more situation is that there are too many regressors and we want to understand which ones are the most important. So it all comes to one task, selecting the most relevant regressors in some sense. So there are three sets of methods for doing this. One set of methods are called subset selection. The other is shrinkage and regularization, and another dimension reduction. I'm not be talking about dimension reduction. It's here on slides, but I will skip it. I will quickly rush through this, and then the most important part will be this. So let us go through subset selection methods. So first is best subset selection. You do a very dumb thing. You just go through all combinations of predictors, or regressors, and use some criterion to select the model that is the best. As simple as it is. The problem, so for the model selection methods, you use either cross-validated prediction error, which I explained in tutorials, or you use a CP or a Akaik information criteria, Bayesian information criteria, or adjusted R-square. So you use one of those criteria. I want to introduce this data set because I'm going to be using it in later in examples with Lasso and Reach. So that example is some real data from a bank. It's called a credit data set that has a bunch of quantitative and a bunch of qualitative variables. Quantitative variables are, it's records about a person who is applying to a bank to get a credit. Quantitative variables are balance, age, number of credit cards, education, income, credit limit that the person right now has, and rating. And qualitative variables are gender, student status, ethnicity. And we want to predict, say, we want to predict the balance, I think, here. But I forgot. Yeah, we are predicting the balance of that person. So here's just one example how we apply best subset selection on this credit data set, where we take some predictors. Like if we take two predictors, these are our residual sum of squares. If we take three predictors, and so on. One thing that you can observe, which you're aware of, the more predictors we have, the lower is residual sum of squares, or the larger is R squared, which is not surprising because we know that it's just mechanically in OLS, the more predictors we have, the lower will be in sample R squared, or the higher will be in sample R squared, sorry, or the lower residual sum of squares. Then that's why we never look at R square when we are choosing models of different sizes with the different numbers of predictors. We use either cross-validation, and so we look at the test error, or we use the Akaike, Bayesian, or adjusted R squared criteria. The numbers, the problems with such approach are that it's computationally expensive, as the number of the number of regressors grows, the number of cases we need to go through grows exponentially. At some point, I was giving a home assignment to students here in Tokyo to use 10 regressors and do the subset selection method. And one student complained to me that his computer burned while he was running computations. Of course, you cannot blame me because something wrong with the computer, but it was just funny. He learned it, or it was he or she, I forgot, learned it the hard way of the computational burden of this approach. And then there are also statistical problems with this approach. If we go through all potential models, we are getting what statisticians call data mining. We basically have a higher chance of fitting models that look good on the training data, and they might not have any predictive power on future data. We might be just catching statistical, so-called statistical flukes. You can look at this this cartoon in your free time, following this link. The point is that we might be catching some plausibly looking regressions, but actually they might not necessarily be good descriptions of the true relationship. Then there are now the next set of methods I'm going to just quickly say and then do not go into details. People came up with all kinds of schemes of stepwise selection methods where you say start with a regression with just one regressor, then you go through all relationships of outcome and one regressor one by one, choose the best one, then you fix that one, you don't touch it, then you add one more and go through all the regressions with two regressors. The first one is fixed, the second fixed, the second one you select, then you select the best model, and then you continue like this. And you stop while you're not making significant progress. This is one way. Another way is you start with the large. This is forward walk. Another way is a backward walk. You start with the largest regression with all regressors, and then you go back. There are also combinations of these approaches, like you go forward 2 steps, backward 1 step. I don't know. People come up with all kinds of schemes. The point is that that was the past, like 30 years ago. You should be aware of it, and you should never apply it because there are better ways, and we're getting there. So here I had it on slides before, the different, if I'm not mistaken, different information criteria, but you should be aware of them, and ideally you should know how they derived. Especially the Bayesian information criteria is quite easy. It's true for linear regressions. Akaike information criteria is a tough criterion to derive. Akaiki is a Japanese statistician. I think he's still alive somewhere around Tokyo or Kyoto. I forgot where he is now. If I'm not mistaken, or did he pass away? I forgot. Anyway, it's a tough criterion to derive, but it seems like it's similar to Bayesian, but actually the derivation is very, very different from Bayesian. It's super hard. But of course, in practice, you just take it off the shelf. The statistical packages compute for you the information criterion. And adjusted R squared is kind of ad hoc criterion that adjusts for the number of regressors.
Do I
Anyway,
remember,
yeah.
do I remember correctly that adjusted R squared is connected to the F test?
I think, yes, it is connected to F test, but again, under certain assumptions. So yeah, I take it back. It's not not fully ad hoc.
I mean, there are some critical values of the F test. We could use them.
I'm not sure about that. There is I mean, sorry, there is a I forgot about. Is there a closed form solution for the R adjusted R squared distribution?
I think yes, if I remember correctly, the idea of the F test is that something like adjusted R squared or the difference of the R squared of unconstrained and constrained models follows a certain distribution, and that distribution has some critical values.
Okay, yeah. I think the problem is that this might be true. I'm not sure. I mean, one thing for sure, you don't use statistical methods for making a distinction between models based on adjusted R squared. So I'm not sure how those critical values help in selecting between the models. Maybe I missed something in my statistical training, but I don't remember anything like that. You just literally compare the values of adjusted R squared. You don't make any inference or any hypothesis testing when you're using adjusted R squared to choose the best model. And that's what's important here. Okay. Anyway, so you use this, it's computed for you. Then, like for example, here, yeah, let me skip this. I want to rush to lasso and I want to rush to lasso and reach. So, okay, there are 20 minutes remaining. Let's talk about reach first. So in the least squares, you're minimizing this loss function. In the reach regression, you minimize this plus shrinkage penalty, so-called shrinkage penalty. Lambda here is called the tuning parameter, and it's determined separately. It's part of your problem. Part of your problem is to estimate of coefficients beta, and part of your problem is to choose lambda. For the rest of these slides, we will be denoting the coefficients beta estimated by reach as beta hat lambda. r, beta hat lambda r. One thing to note is that there is no penalty for beta 0, so the summation starts from j. One reason for this is that we don't shrink the intercept. I mean, the reason for this is that we don't shrink the intercept, which is the mean value of the response when all the regressors are 0. And there is no reason to there is no reason to shrink the mean. And so what we do with reach, we minimize this, we fix lambda to some value, like say 5 or 0.1, and we minimize this a residual sum of square plus shrinkage penalty. Observe here that we are taking coefficients to the power of 2. One note with the rich regression, one important note is that we need to be careful about scaling of parameters. Here's the deal. With the least squares, we never care about the scales of parameters. We can say if we are running, I don't know, price of an apartment on the square meters of an apartment, a regression like that, we can be pricing apartment in rubles or dollars or euros, thousands, millions. We can be using square meters, square centimeters, square kilometers. It doesn't, a square feet doesn't matter for the OLS regression, because simply scaling just cancels out. We will just get different coefficients beta, but the interpretation stays the same. With the reach regression, it's now different, because if we change scales, then some coefficients beta would be smaller, some will be larger, and we might be shrinking more aggressively the larger coefficients. So, which means that we somehow need to make all X regressors comparable. And usual way is to use standardized predictors or regressors by scaling them like so, dividing them all by their variance and making them, yeah, by their dividing them by variance, in sample variance. Yeah, that's all I want to say. I want to say more, but it's not the right time to say more things. So let's go now to the created data set. So here in this picture, we are looking at the coefficients. We standardize all the regressors, and we are looking at beta p, or let's say p is the number of regressors, k, lambda k for different regressors. And so what you see here is that so there are these gray lines. There are all regressors included here. The gray lines are everything but these 4 most important regressors. We see that when lambda is equal to 0, close to 0, then we get large values of these key regressors, for the coefficients of the key regressors. This is basically when lambda is small, we are basically getting close to OLS estimates. As lambda increases, the coefficients go to 0. They don't go monotonically. Like, for example, for the coefficients for the rating, it increases first and then falls. But overall, they tend to shrink to 0. And when lambda is very large, they all converge to 0. Yeah, I will skip this figure. It's just a different way of looking at these coefficients. It's the coefficient relative, again, standardized coefficients. And this is the measure of squared sum of square root of the squared sum of the coefficients for reach divided by OLS. It's another way of looking at these coefficients. When lambda is very large, they all collapse to 0. When lambda is small, they give us OLS coefficients. So this object is equal to 1, and it always varies between 0 and 1. Okay, now this is a good time to talk about bias variance trade-off. So here in this picture, on this exercise, we are looking at a simulated data set with 45 predictors, 50 observations. All of the predictors are relevant, but note that the number of observations is of the same order as the number of predictors. Now we do the reach, and this mean squared error is calculated this expected value of y. So we do like a billion of simulations and calculate the average to calculate this object. We do it like a billion of times. Draw 50 predictors, 45 predictors, construct 50 observations, run the regression or run reach, calculate the outcome minus prediction, save, and do it billion times, calculate the average. Then the average error is the which one? The purple line, this one. As we change lambda from 0 to a large value. So let us focus on this purple line first. Let me use a different pen. So even though all predictors are relevant, as we increase lambda, we are getting smaller mean squared error. And then at some point it starts increasing. But the point is that the optimal lambda will not be 0. It will be like 1 or even 10. It's 10 here. Now we can decompose this into variance and squared bias. So this part is fixed, sigma squared. Nothing happens to it. While these two guys are changing as we are changing lambda. Let's start with the bias. When lambda is 0, bias is 0. This is OLS. We know that OLS has 0 bias. As we keep increasing lambda, bias doesn't increase much and then starts shooting up. At the same time, variance, it starts from here, but then as we increase lambda, it keeps falling. and then at some point we get the best value of lambda. Let me iterate, let me emphasize. All 45 regressors are relevant. However, by shrinking them to 0, we achieve a better prediction in terms of the risk, because we decrease variance and we don't increase bias that much. Why it works here? Because the number of observations is small. Suppose the number of observations is 500, then perhaps this wouldn't work. Perhaps the optimal, in the sense that the optimal lambda will be closer to 0. Okay, that was reach. Now, what is lasso? Almost the same, except for instead of in reach, we use beta j squared. Here we use the absolute value. That's mathematically, that's the only difference. Lambda again is the tuning parameter. Larger is lambda, more we shrink the coefficients. Lambda is 0, we are back to OLS. Amazingly, lasso has very different properties from reach. By just changing it to the absolute value, we get some, I would say, amazing statistical properties that I'm not going to discuss. There was in the past 5 years, there were huge breakthroughs in statistics in terms of establishing some statistical properties of lasso. And lasso has been around for some time, like for, I think, perhaps 20 or 30 years, maybe 20 years for sure. But it was only recently there were some big breakthroughs in establishing some statistical properties of this guy. And for the people who used it, they used it not for the statistical properties. They use it for this very nice property that lasso tends to shrink coefficients exactly to 0. Reach regression never gives you exactly 0 coefficients. It can have very small values of the coefficients, but never exactly 0. Lasso can shrink coefficients exactly to 0. So in that sense, we say that lasso yields sparse models, models that involve only a subset of the variables. Here's an example with the credit data set. Again, we change lambda here from 20 to 5,000. And for the coefficients for the standardized values, we see that, say, for all the gray lines, they start small and then they collapse exactly to 0 at some point. For other variables, they also one by one collapse to 0. And this one is, I think, the rating. Yes, that's the rating. It collapses to 0 the last. And so, and this is the nice property of lasso. Now, why it collapses to 0? So first of all, let us compare reach and lasso with subset selection methods. We can write reach like this, lasso like this, and subset selection methods are like this. So we are minimizing the sum of squared errors subject to this constraint in reach. You can see that gives you the original reach by writing the Lagrangian of this problem. So that would be the Lagrangian of this problem. you can drop this part because it's not important. The same for the lasso, and the same, and for the subset selection method, you can think about it as minimizing the sum of squared errors subject to the number of coefficients that are not zero. So this is an indicator function. And so we can, in that sense, we can interpret reach and lasso as computationally feasible alternative to the best subset selection. So basically, we replace this by either this constraint or this constraint. Now, here's an explanation why lasso leaves some coefficients, makes some coefficients exactly zero, and why reach never leaves coefficients equal to zero. So this is an example with two regressors. For the lasso, in this two-dimensional space, the lasso constraint set is this diamond, while the reach regression constraint set is this ball, circle. And then these contour lines are different levels of the objective function the levels of the objective functions of the constant error. I'm saying it correct? I'm getting tired. But basically, we fix this to say C, and then that would be that these ellipses would be all combinations of beta 1, beta 2 for different levels of C. And if C is very large, then we are here, and we can do better. If C is very small, then we are here, but we don't satisfy the constraint. And then the constraint is satisfied where we touch the diamond, the constraint set. And we can, if we are at the corner, we get that the coefficient is exactly zero. While with the ball-like or circle-like constraint set, we never at the corner. We always, unless we in some pathological situation like this, or like something like this. So that's why we never get a coefficient exactly zero with reach. So I see I'm almost out of time. Let me see, I want to say anything. The last thing I want to say that in practice, there are lots of computational methods that efficiently calculate loss and reach for whole range of lambdas. So you can use some efficient calculations for that. How you choose lambda? One way to choose lambdas would be use the most widely used way is to do cross-validation. So you divide your set into test, training and set. You train it for different values of lambdas, and then you compare the performance on the test data set. And another way would be to do some information criterion, but I think like doing something like the only thing you can do here, something like a kike information criterion, but you need to write down the likelihood function, and that might be super difficult. That's why people are using just the cross validation to choose the tuning parameter. And the usual procedure would be you go through the grid of tuning parameters. You use cross validation to find the one that gives the best performance on the test data set. And then you re-estimate the whole model on the full data set. And that would be your model for forecasting. Okay, so I think there is more on the slides, but I said everything I wanted, the essence. So we finish here. We will work more with ridge and lasso and with univariate models during the tutorials this coming Saturday. And then the next lecture we will talk about trees, regression trees, random forests, boosting trees, and VRs. And then that would finish it. Okay?
Okay.
So this Saturday, it will be the same thing, and we'll have seminars at 9:30.
Yeah, like I don't know, like last seminar only Nikolai came. I cannot do, I just cannot. It's like there was literally only one person. I just I refuse to. I mean, if I told you if you want, you can choose. I'm relatively flexible on Saturday, so if you come up with the schedule that like all of you can come, I'm happy to adjust. But I'm going to do it only once. Because again, literally there was last time there was only Nikolai.
We are not very flexible at Saturday because we have another seminar and then a lecture at this time. So I don't know only if we do a seminar even earlier, but then again, it's not exactly optimal to do a seminar at like 8 o'clock.
Well,
I
I don't
don't
know.
know.
It depends on how much you want. When I was at PhD, our lectures started at 8 a.m. And that was normal. When I was at the New Economic School, our lectures started at 9:30, I think. At 10, but it was taking an hour to get there. So I was usually going to bed at 3 a.m. or 4 a.m. I was having like a few hours of sleep, was waking up at 8:20. Yeah, and I was waking up at 8:20 and I was at school by 9, right? 9:30 the lecture started. Yeah, something like that. Anyway, starting earlier is not an option, is not an argument for me. All of my life I was around people who were, including myself, going, and when I was at Novosibirsk State Universities, our lecture started at a.m. for like 4 years. So I don't know what you're talking about.
There was a seminar at 11, so we need at least an hour to get there. So
I see. I
yeah.
see. That's what you mean. Yeah, I don't know. I don't know. It's Fyodor, I understand. I feel your pain, but if I do the seminar, okay. Um, First of all, for me, it's like 12 a.m. at night, and I come, and only you will come. And at least I do it earlier so that I don't torture myself with staying up in my office till 12 a.m. So if you guarantee to me like that 20 people will come and all participate, of course I will be happy to do it.
I just hope that I will be able to complete the project, and I think we had something else. Some other assignment. I hope I will be able to do that.
Ask Nikolai. He's the expert now.
By the way, can I ask a quick question about the assignment?
Sure.
Well, the thing is, I thought the data was exactly like in the empirical exercise in Elliott and Timmerman. But I got the results, and the relationship between the classical and the Bayesian methods are as expected. I mean, the inference and stuff. But the levels, I mean, the exact values are different by like, I don't know, 30% compared to the picture in the textbook.
That can happen because you are using. I don't think like they're using different data. For the picture, they're using a different measure of the risk-free rate, and also are they doing it for the same time period? I'm not sure.
Well, it's between 1994 and 2013, so I thought so.
I see. So, and the difference in risk-free rate cannot be that large, I guess. Although they're using a different risk-free rate, but it shouldn't matter that much. So you're saying that you're getting. So one thing to check that if you're getting the right thing or not is to increase the number of integration points. For example, your I go from like how many do you take?
I take 90,000, but I tried more, and it's pretty robust.
Pretty robust.
I mean, it's flattening out at like around 40%, and in their picture, it's around 75%.
I see. I see.
So, well, maybe that's because they're using some different data. Well, I just wasn't sure. I think it's okay.
It might be. It's okay. It's okay. Do you have the codes? I can take a look at them. I mean, if you show me now, I can take a look and see what you're getting.
Yeah, okay, I can.
Okay.
Well, let me share the screen.
Yeah. Yeah. Okay, share your screen.
Okay. Then I'm stopping your demonstration.
Yeah.
Right. Yes. Well, I get this picture. And
okay.
I think it seems okay, but
yeah.
the levels are a bit, not a bit, but quite a bit lower than
from the book, right?
Sure. Yes.
Right. Okay. So, right. Now, go show me how you do the classical estimation.
Okay.
Okay, that's where it starts, right?
Yes.
Okay, let me see.